In this video, we're writing proofs by mathematical induction, higher level only. And I want to start by showing you why you need it, because the obvious alternative looks like it works. Here's a formula: n squared plus n plus 41. Put in 0, you get 41, prime. Put in 1, 43, prime. 2 gives 47, prime. And it keeps going. 3 gives 53. 4 gives 61. It is prime for n equals 0, all the way up to 39. 40 values in a row, no exceptions. At that point, you would be forgiven for calling it proved. And at 40, it dies. 1600 plus 40 plus 41 is 1681. And that is 41 squared. Not prime. 40 correct cases prove nothing at all. That is the same point the deductive proof video made. Checking values is not proving. Induction is the tool that actually closes that gap. And it does it in 3 steps. Step 1, the base case. Show the statement is true for the first value of n, usually 1. Step 2, the inductive step. Assume it is true for n equals k, and use that assumption to prove it is true for n equals k plus 1. Step 3, the conclusion. Write the concluding sentence. All 3 are worth marks, and step 3 is the one people skip. Now the objection everybody has the first time. It looks like you assumed the thing you were trying to prove. You didn't. You assumed it for one particular value, k, and what you actually proved is an arrow. If it is true for k, then it is true for k plus 1. That arrow on its own proves nothing, because you don't yet know it is true anywhere. That is what the base case is for. Think of dominoes. The arrow says each domino knocks over the next one. The base case pushes the first one. You need both. With only the arrow, nothing ever starts falling. With only the base case, you have checked one value, and we just saw what 40 checked values are worth. And this is the sentence you write at the end. True for n equals 1 and true for n equals k implies true for n equals k plus 1. So by the principle of mathematical induction, it is true for all positive integers n. Learn it. Write it every single time. It is a mark, and it is the easiest one in the question. Example 1, the standard one. Prove that 1 plus 2 plus 3, all the way up to n, equals n times n plus 1 over 2. Base case, n equals 1. The left side is just 1. The right side is 1 times 2 over 2, which is 1. True. Now assume it is true for n equals k. So 1 plus 2 up to k is k times k plus 1 over 2. And write down the target before you start. For k plus 1, we want k plus 1 times k plus 2 over 2. Now the step. Take the sum up to k and add the next term, k plus 1. That is k times k plus 1 over 2, plus k plus 1. Factor out k plus 1. That gives k plus 1 times k over 2 plus 1, which is k plus 1 times k plus 2 over 2. And that is exactly the target. Then the concluding sentence. Example 2. A different flavor. Divisibility. Prove that 3 to the 2n minus 1 is divisible by 8. First, tidy it up. 3 to the 2n is 9 to the n. So the statement is 9 to the n minus 1 is divisible by 8. Base case, n equals 1. 9 minus 1 is 8. Divisible by 8. True. Now assume 9 to the k minus 1 equals 8m for some integer m. The step. 9 to the k plus 1 minus 1 is 9 times 9 to the k minus 1. And here's the move. Add and subtract to manufacture the thing you assumed. That becomes 9 bracket 9 to the k minus 1 close bracket plus 8, which is 9 times 8m plus 8, which is 8 times 9m plus 1. 9m plus 1 is an integer, so that is divisible by 8. And that move is worth naming, because every divisibility induction is that same trick. Example 3, an inequality. And this one has a trap sitting in the base case. Prove that 2 to the n is greater than n squared, for n greater than or equal to 5. So why not start at 1? Test it. N equals 4 gives 16, and 4 squared is 16. 16 is not greater than 16. They are equal. So the statement is false at 4, and the base case has to be 5. Base case, n equals 5. 2 to the 5th is 32. 5 squared is 25. 32 is greater than 25. True. Assume 2 to the k is greater than k squared, for some k at least 5. The step. 2 to the k plus 1 is 2 times 2 to the k, which is greater than 2k squared. And now it is enough to show 2k squared is at least k plus 1 squared. Rearrange that and you get k squared minus 2k minus 1 greater than or equal to 0, which holds for k at least 3, and our k is at least 5. So 2 to the k plus 1 is greater than k plus 1 squared. The lesson here is simple. Always test the first few values. Starting the base case in the wrong place is a proof of nothing. Example 4. And this one ties the last 3 videos together. Prove de Moivre's theorem. Cos theta plus I sine theta, all to the n, is cosine n theta plus I sine n theta. Base case, n equals 1. Both sides are cosine theta plus I sine theta. True. Assume it holds for n equals k. The step. Cosine theta plus I sine theta to the k plus 1 is the kth power times one more factor. By the assumption that is cosine k theta plus I sine k theta times cosine theta plus I sine theta. Expand it. You get cosine k theta cosine theta minus sine k theta sine theta plus I, bracket, sine k theta cosine theta plus cosine k theta sine theta. And those two brackets are exactly the compound angle formulas, which are in your formula booklet. So that is cosine of k theta plus I sine of k theta plus theta, which is cosine k plus 1 theta plus I sine k plus 1 theta. And notice what is actually driving that proof. It is the rule from 2 videos ago. Multiplying complex numbers adds the arguments. Last video we used de Moivre. This is where it comes from. Now, the calculator. And this video is a deliberate exception. Your calculator will happily confirm that 1 plus 2 up to 20 is 210, and that 2 to the 10th is greater than 10 squared. Use it for exactly that. Checking your base case arithmetic, insanity checking that the k plus 1 target you wrote down is the right one. What it cannot do is the proof. A calculator checks cases, and this video opened with 40 consecutive correct cases that meant nothing at all. So here, the machine is a proofreader. It is never the argument. Base case, inductive step, concluding sentence, and write the sentence every time. Next video is the other proof method on the syllabus. It works by assuming the opposite of what you want and watching it fall apart. Proof by contradiction.